I guess for a brief introduction, everyone knows what prime numbers are. They're things, they're numbers which only have the divisors of 1 in themselves. So like numbers like 2, 3, 11, 31, 67. Oh, right, Naveen's recording. Yeah, that's a good call. And basically there's, I think, 25 prime numbers less than 100 that you should probably memorize. And let me pull them up. Yeah. So here's a list of the prime numbers up to 150. So there's 25 from 1 to 100. And then a further, let's see, another 11 primes between 150, or another 10 primes between 100 and 150. So memorizing all of these would be pretty useful for competitions. If you don't want to memorize the ones above 100, definitely memorize the ones below 100, and also the number of primes. That's going to be really useful as well. So how do we figure out if a number is prime? So usually you would probably just check all the numbers from, or rather all the prime divisors from 1 to that number. So let's say we're trying to figure out if 68 is prime. Let's see. 6. All right, hold on. All right, 68. If we're trying to determine if this number is prime, we're going to be checking all the prime numbers to see if it can divide into it. So we can start off 2 already divides it. 2 already divides it. We also know that 17 divides this number as well. So it's obviously not prime. But let's say we have something like 71. We can try 2, 3, 5, 7, 11, 13, all the way to what, 67. And we realize that none of these prime numbers divide 71. So 71 must be prime. You might be thinking, well, that's like a really tedious process. How do we make this faster? The way to speed up this process is, instead of checking all the prime numbers up to 71, we can just check the numbers up to the square root of 71. And that'll be much faster than going through all the primes up to 71. So like the square root of 71 is, it's like between 8 and 9. So we only have to check the prime numbers 2, 3, 5, and 7. And obviously, like for 71, this is a really small number, but this is more especially useful for larger numbers. Oh, looks like Kevin's here. Hold on, give me a second. Oh, never mind, he's not on yet. But like I was saying, this is more useful for larger numbers. Like, let's say like, I don't know, 256, or not 256, that's it, 257, or something like that, which you don't know if it's prime or not, but you can check all the prime numbers up to something like 17 or 16 or 15 instead of going all the way up to 200. So that's especially what this is useful for. And so moving on, now that we know how to determine if a number is prime, let's talk about factors. Oh, and yeah, now Kevin's here. Let's see. Let me make him co-host. Or wait. So now that Kevin's here and Naveen is here, I guess you can ask either of them questions. I don't know if Naveen will be leaving, but yeah, feel free to ask questions to either one of them. Yeah, continuing on. Let's try a quick problem in relation to prime numbers. So this problem asks for every integer n greater than or equal to 2, let this function pow n be the largest power of the largest prime that divides n. So for example, 144 is equal to 2 to the 4th times 3 squared. So therefore, since 3 is the largest prime, we take the exponent of 3, which is 2. So therefore, power 144 is just 3 squared, which is 9. And basically, before we tackle this, actually, let me go over quickly the concept of prime factorization, just in case you're not familiar. Prime factorization is basically the process in which we take a number and we divide out primes. Basically, that's, let's say we have, let's just use the example 144 that was in the problem. So basically, we try to divide out as many primes as we can until we get to 1. So this is equal to 2 times 72. It's equal to, and 72 is equal to 2 times 36. 36 is equal to 2 times 18. 18 is equal to 2 times 9. 9 is equal to 3 times 3. So we have 4 powers of 2 and then 2 powers of 3. So this is just 2 to the 4th times 3 squared. 3 squared, there we go. So yeah, I just want to briefly mention that in case you weren't familiar with the concept of prime factorization. But moving on. Wait, crap. So how do we make use of this function POW in order to determine the largest number that 2010 to the m divides this this product? And this product is basically, if you're not familiar with this fancy pi-looking symbol, it's basically asking for the product of POW 2 times POW 3, and then you multiply it all the way up to POW of 5300. That's what this symbol means. Basically, the 2 at the bottom is where you start. The 5300 at the top is where you stop. And so in order to find this, we basically want to see how many times 2010 to the m divides this. So let's first factorize 2010 to the power of m. Let's first factorize that in order to make it possible. Try to write softer. Okay, I'll keep that in mind. On it, I'm not usually writing on this. It's really insensitive because my iPad isn't available right now. That's why it's kind of whack. But basically, Jesus Christ. 2010 to the m. Well, this is equal to 2 to the m times 3 to the m times 5 to the m times 67 to the m. And so basically, now that we have this prime factorization, we realize that the only thing we are really looking for is how many times that 67 to the m can divide into this expression right here. Actually, let's just call this P for simplicity's sake, so I don't have to keep referring back to it. So how many times, and the reason we only look for 67 is because these other prime numbers, they're so small that they're kind of irrelevant. So we only really need to worry about the 67. And then how do we actually determine how many times 67 is in this, actually shows up in this P? So basically, let's take a look at 5300. 5300, this is greater than, or let me write on the other side. 5300 is greater than 67 times 79, which is 5293. So 67 times 79 is the largest number, which has 67 that is less than 5300. And basically, we want to find every number of the form 67 times x, such that x is whatever, but 67 is the largest prime number, it's the largest prime factor. So that's why we look at this expression right here. So 79 is the largest number that x can be. So that means that for every number from 1 to 79, it's going to provide us with one copy of 67 to P. However, there are a few exceptions. So most notably, if we take a look at 79 itself, 79 is actually a larger prime than P. So we actually don't count it. And also, other primes are 61, sorry, not 61, 71, 73, 79. These actually all don't work. So if we take the 79 total cases, let's go up here, 79, we subtract 3. This is equal to 76 cases. And you might be thinking that this is our final answer. However, there's also one other exception, and that's 67 times 67. And the reason that's an exception is because if we have 67 times 67, it will contribute 2 copies of 67 to P. So instead of subtracting 1, we add 1 back. So the final answer would be 77. Yeah, hopefully that makes sense. So basically in this problem, we just took advantage of our understanding of this power P and how we can just basically ignore all of these other prime factors and only focus on 67. And the tricky thing is just to notice these exceptions, right? Because this is an AMC problem and it's multiple choice. So you could easily just go 79 or 76 or something like that and get it wrong. So let's move on. So let's talk about the number of factors that something has. Ignore this at the top for now. Ignore that for now. Basically, if we want to determine the number of factors that something has, we need to first prime factorize it. So let's say we have a number n. This is equal to something like P1 to the A1 times P2 to the A2 times P3 to the A3 times all the way to Pk to the AK. So there's a total of k primes in the prime factorization of n, and each of them has its own exponent, which may or may not be distinct. So basically, in order to determine the total number of divisors that n has, we just take each of these exponents, we add 1 to them, and then we multiply them together. So this is A1 plus 1, A2 plus 1, times ... all the way to AK plus 1. So this expression is equal to the total number of factors that n has. And this in itself is a pretty well-known formula, but the number of applications it has is very expansive. So we're actually going to be going over 3 different problems which take advantage of this specific formula right here. So let's start off with this one. So this question asks, how many perfect squares divide 16 factorial? And this is not quite what we had earlier. It's not quite asking for the number of factors. It's rather asking for the number of factors that are perfect squares. So let's first start off by prime factorizing 16 factorial. 16 factorial, this is equal to 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10 times 11 times 12 times 13 times 14 times 15 times 16. And if we prime factorize each of these, this will give us 1 times 2 times 3 times 2 squared times 5 times 2 times 3 times 7 times 2 cubed times 3 squared times 2 times 5 times 11 times 2 squared times 3 times 13 times 2 times 7 times 15 3 times 5, and then finally 16, which is 2 to the 4. So if we combine all of these exponents, this will give us a total of 2 to the 15 times 3 to the 6 times 5 to the 3 times 7 squared times 11 times 13. So if we were traditionally going to ask for the total number of factors that this number has, then we'd be looking for 16 times 7 times 4 times 3 times 2 times 2, since that's just what we get when we add 1 to each of these numbers. However, we're asking for the total number of perfect squares which divide 16 factorial. And the special thing about perfect squares is that their prime factorization, all of the exponents are even numbers. That means we're only looking for numbers which are of the form 2 to the, let's say 2 to the j times 3 to the k times 5 to the p times 7 to the q times 11 to the r, or let me write q, r times 13 to the s. And basically each of these variables, j, k, p, q, r, and s, must be even. And that's what makes the factors perfect squares. So we just now need to calculate the number of options we have for each variable and then multiply them all together in order to find the total number of perfect squares that divide 16 factorial. So for j can go from 0 to 4. Oops, let me rewrite that. 4, 6, all the way to 14. This gives us 8 options. 8 options. K can go from 0 to 4, 6. That is 4 options. P can be 0 or 2. That's 2 options. Q can also be 0 or 2. This is also another 2 options. And R and S have to be 0. So this is 1 option. And so if we multiply all of these numbers, that's 8 times 4 times 2 times 2. This will give us 128. And that's the number of perfect squares which divides 16 factorial. Right, so moving on. Let's try this problem. So this is from the 2016 AMC 10A. It asks for some positive integer n, the number 110 times n cubed has 110 positive integer divisors, including 1 and the number 110 times n cubed. How many positive integer divisors does the number 81 times n to the 4 have? So for this number, let's start off by, again, as is a common recurring theme in these problems, factorizing 110. So 110 is equal to 11 times 10, which is 2 times 5 times 11. So if we have 110 n cubed, this is equal to 2 times 5 times 11 times n cubed. And that's simple enough. So it then states that this number has 110 positive integer divisors. That means that this number is going to be in the form of P times Q times R, let's say A, B, C, such that A plus 1, B plus 1, C plus 1, this number is 110. And also keep in mind there could be more primes like S times T. But I'm just saying that basically from the formula, 1 plus the exponents of all of the primes and the prime factorization of 110 times n cubed has to be equal to 110. And the reason that this is important is because let's say we have just 2, 5, and 11. Then that means 2 to the A times 5 to the B times 11 to the C. That means that A plus 1, B plus 1 times C plus 1 is 110. And we already know the prime factorization of 110. So that means we can assign one number to each of these. So let's say A plus 1 is 11. b plus 1 is 5, and c plus 1 is 2. So that would give us a is equal to 10, b is equal to 4, and c is equal to 1. So that means that the prime factorization of 110 n cubed is equal to 2 to the 10 times 5 to the 4 times 11 to the first. Does that make sense? And the reason that we only use these 3 primes specifically is because they're already present in this factorization. If we include any other primes, let's say we have something like 7, then that means we'd have to multiply by 1 more number. But the prime factorization of 110 is only 3 numbers. So that means we can only have 3 primes. And those are the 3 that show up here. And also another thing to note is that it doesn't have to necessarily be in this order. It could be something like 5 to the 10 times 2 to the 4 times 11 to the 1. And that would work as well. But in this problem, it ultimately doesn't matter. And the reason for that is because if I move down a bit, the reason for that is it's asking us for n cubed, and then we're going to multiply that by 81, or we're going to multiply n to the 4 by 81. And 81 is 3 to the 4, which is a number that doesn't show up in this prime factorization already, which means that it won't really matter. It won't really matter which one of these we use. Which one of this is really bad. Which one of these we use? Yeah. So let's say for the sake of simplicity, we'll just use this first one. So we can now calculate n. So if we divide both sides by 110, which is again 2 times 5 times 11, this is equal to, you get that n cubed is equal to 2 to the 9 times 5 to the 3 times 11 to the 0. And so if we take the cube root of both sides, we get that n is equal to 2 cubed times 5. So now the problem wants us to calculate the number of positive integer divisors that the number 81 times n to the 4 has. This is a 3, yeah. So this is equal to 81 times 2 cubed times 5 to the 4. So this is equal to 81 times 2 to the 12 times 5 to the 4. And again, we can factorize this 81, so that's 3 to the 4 times 2 to the 12 times 5 to the 4. And the total number of factors that this number has will just be from the formula 4 plus 1, 12 plus 1, again 4 plus 1, and this is equal to 325. That's our final answer. Okay, yeah. I just got my iPad back, so give me a moment. Let me switch over to that so y'all don't have to suffer through this horrible writing anymore. Yeah, just give me a second. In the meantime, you can try this problem, I guess, if you're bored. Testing, can you hear me? Okay. Let's see. Let me stop sharing on my. Then let me share my screen here. Oh my God, that's so much better. That writing on a laptop screen is so painful. Okay, back to our regularly scheduled broadcast. You've probably had a bit of time to read over this, so I'll go ahead and jump into it. Basically, this number is asking, or if we want m to have 4 positive integer divisors, that means the number has to be of the form p cubed. And this way it will have 3 plus 1 is equal to 4 positive integer divisors, or it will be something like p times q. So then have 1 plus 1 times 1 plus 1, which is also 4 positive integer divisors. So we want the number m to have either one of these forms. And we can look through both cases. So in the first case, let's first tackle this one. So this means that m has to be some number cubed. So the closest number to our set here, 2010 to 2019, that would be 13 cubed, which is 2197. However, this number is already too big, so the sum of its divisors will be way greater than the set of numbers we have, so that wouldn't work. And then the prime below that is 11 cubed, which is 1331. So we could try this and do the sum of its divisors. However, this is way too small. If we add all divisors, 121 plus 11 plus 1, it doesn't even come close to 2000. So basically this first case right here, it doesn't work. We only have this second case to go off of. So that means that the sum of the divisors of a number like this would just be pq, it'd be pq plus p plus q plus 1. That'd be the sum of the divisors of straightforward if you attended our past lectures. If you don't, you can just, my broadcast just stopped. That's interesting. Let me try that again. Okay, great. So where were we? Oh yeah, so basically this number p plus 1 times q plus 1 must be equal to some, it's asking how many numbers in this set can equal p plus 1 times q plus 1. And so, like I got kicked off.
She hates you.
Even number. So It just keeps stopping again. That's interesting. Okay, technical difficulties. Oops. Let me try and rejoin the meeting, I guess. Okay, I'm back. Hopefully it's a bit better this time. Sorry about that. Okay, let's try this again. Hopefully it doesn't crash on us. Don't know what the problem is. It's very weird. Here we are. Okay, so as I was saying, this number has to be the product of 3 times some even number, which means it's a multiple of 6. And the only numbers in this set from 2010 to 2019, which are multiples of 6, the only numbers are 2010 and 2016. So let's consider those 2 numbers. Let's move the screen down again. So let's first take a look at 2010. So if 2010 is equal to 3 times, let's say, q plus 1, that means 2010 divided by 3 minus 1 is equal to q. And I'm not gonna do this calculation, but basically this number is not prime. Not prime. That's why this case doesn't work. And then if we try 2016 is equal to 3 times q plus 1, and then we do 2016 divided by 3 minus 1, or yeah, this will also not work. Also not prime. So therefore, neither of these cases will work. So that means one of P or Q cannot be 2. So that means we have to take a look at a separate case where both of them are odd primes. Let's move down once again. So if both of them are odd primes, we have some odd number plus 1 times some other odd number plus 1. This will give us a number which is divisible by 2 times some number which is divisible by 2. So that means n has to be divisible by 4. So the only numbers which are divisible by 4 in the set 2010 to 2019 is, let's see, 2012 and 2016. So let's take a look at these two cases again. So let's first look at 2012. 2012 is equal to 4 times 503. It only has at most 2 factors of 2. And that means that our first option is that we have p plus 1 is equal to 4 and q plus 1 is equal to 503. However, this won't work because this gives us q is equal to 502, which is not prime. Our second case is if we split this up. This is equal to 2 times 1006. So that will give us, down a bit, that'll give us p plus 1 is equal to 2 and q plus 1 is equal to 1006. This obviously also does not work because this means that p is equal to 1, which is also not prime. So 2012 won't work here. And let's try 2016 now. (2016) is equal to 4 times 504. And so that means that we can have p plus 1 be equal to 3, or sorry, p plus 1 be equal to 4, and q plus 1 be equal to 503. And, 504. Therefore, p is equal to 3, which is prime, and q is equal to 503, which is also prime. And going back to what we talked about at the beginning of this class, you can check 503 is prime by checking all of the prime numbers up to square root of 503 to see if it divides 503. If none of them divide it, then that means 503 is prime, which it is. So therefore, 2016 is the only number which is a nice number. So therefore, our final answer is 1. All of the other numbers don't work, as we've shown through our testing. So for this problem, we did the sum of the divisors by just doing pq plus p plus q plus 1. And that was actually a very straightforward way to calculate the sum of the divisors because we only have 4 divisors. But if we have more than 4 divisors where they aren't specified, then that becomes a lot harder to do. Luckily, we have a formula to help us. So this formula states that given a number n is equal to p1 to the a1 times p2 to the a2 all the way to pk to the ak, the sum of the factors of n is just 1 plus p1 squared all the way to p1 to the a1 multiplied by the same expression for every prime. So if I give a quick example, let's use 36. 36 equal to 2 squared times 3 squared. So the sum of the divisors of 36, let's say p1 is equal to 2, and then p2 is equal to 3. Then the sum of the divisors would be 1 plus p1, which is 2, plus p1 squared, which is 2 squared. And we would keep going, but we stop at 2 because that's already the largest power of 2 in 36. And then we do a similar thing for 3. So that's 1 plus 3 squared. And this would be 7 times 13, 91. And that would be the sum of the factors of 36. And that was just a very basic example. Let's try a slightly harder one. This problem asks, how many numbers less than or equal to 100 have the sum of their factors equal to an odd number? So this problem, if we want the sum of the factors equal to an odd number, then we want each of the p expressions. Oops, let me rewrite that. We want each of the p expressions, 1 plus p1 plus ... 1 plus p2 ... We want each of these to be odd. Because if we have a single even number, then it makes the entire product even. So therefore, all of these have to be odd. And let's say we have one of the prime numbers equal to 2. P is equal to 2. then that means we have 1 plus 2 to the 1 plus 2 squared plus dot 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 plus 2 to the ak, whatever. Each of these is going to be even, and then we have this 1 here. So this expression will be odd. So if p is equal to 2, this expression will always be odd. So now what happens if p is not 2? If p is not 2, then we have something of the form 1 plus an odd number. Let's just say 3, for example. 3 to the 1 plus 3 squared plus dot 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 plus 3 to the ak. So since each of these numbers will be odd, we need the total number of these to be odd as well. So that means that ak has to be even. Since if we go from 0 to ak, this gives us odd. This gives us the total number of odd terms. So now that we know that ak has to be even, or p is equal to 2, then that turns the problem into asking for how many perfect squares times some power of 2 are there less than 100. And the reason for that is because if ak is even, then like I mentioned before, all perfect squares have their exponents in the prime factorization to be even as well. So therefore, it'll be some number squared times 2 to the p, or p is a bad number. Let's say 2 to the x. And this is, we want all of these numbers that are less than 100, or less than or equal to 100, as the problem states. However, we can further simplify this by noticing that 2 to the x is either a square itself if x is even, or if x is odd, then it's equal to 2 times some number squared. So therefore, we're asking for the total number of numbers which are either perfect squares or 2 times a perfect square. And the number of numbers which are like that, less than 100, we can just list them all out. So the numbers which are perfect squares are 1 squared, 2 squared, all the way to 10 squared. That's 10 numbers. And then for the numbers which are 2 times a perfect square, we have 2 times 1 squared, 2 times 2 squared, all the way to 2 times 7 squared, which is 98. So if we go any higher than that, we'll be above 100. So this is 7 numbers. So if we combine these two, that makes our total answer 17. So the key to this problem is noticing that we want each of these expressions involving p to be odd, and then splitting it into cases. And that's something you're going to see with a lot of number theory questions that involve primes and factors, that you're going to have to do a bit of casework, because the 2 tends to throw everything off. Sorry if I'm rushing a little. We're kind of like cutting close on time since we had some technical difficulties. So make sure if you have any questions to ask Naveen or Kevin. Okay, so now let's talk about the product of the divisors of a number. And the way that this formula works is that if we have a number, let's once again use 36 as an example, because I like the number. We have 136, 218, 312, 49, and then 6. So the key is noticing that each of these, when you multiply it, is equal to 36. So if we multiply each of these, we get 36. And this is left alone, which is 6. So therefore, we just take the total number of divisors that a number has. We divide it by 2, because that represents pairing them up. And since each one of them multiplies to 36, we have 36 times 36 times 36 times 36 times 36 to the 1/2. So each pair of factors will contribute 136. And in the case that there's left over, it will just be square root of 36. So therefore, that's why this formula works, because we have the total number of divisors, we pair them up, and then each one contributes a copy of the number itself. And this also works for numbers which have an uneven number of factors are also perfect squares, because if we have something like let's say k is odd, then if we just take if we omit the square root, then we'll just have k minus 1 over 2 pairs. So we raise that to the n power, and then we multiply by n to the 1/2, which is the thing we omitted, and this gives us n to the k over 2 anyway. So the formula works regardless if k is odd or even. Let's try this with a quick problem. This problem asks for the sum of the base 10 logarithms of the divisors of 10 to the n, and it tells us that this number is 792, and it asks us for what n is this possible. So if you've been to one of our previous classes, I think it was Naveen, he talked about how in logarithmic properties, if you have something of the form log b(a)(1) plus log base b(a)(2), this is equal to log b(a)(1) times a2. So if we have the sum of the base 10 logarithms, then that's just the product of the divisors, if that makes sense. So let me write it out actually. Let's say the divisors are d1, d2, d3, all the way to dk. Then we have log 10 d1 plus log 10 d2 plus dot 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 plus log 10 dk. And using this property right here, this is just equal to log 10 times log 10 of d1 times d2 times d3 times dot 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 times dk. And so basically now we just need to find an expression for this. So if we have 10 to the n, this is prime factorized as 2 to the n times 5 to the n. Oops, that's a bad 5. Times 5 to the n. This means that we have a total of n plus 1 times n plus 1 divisors. So if we make use of the formula, then this expression right here becomes 10 to the n to the power of n plus 1 squared over 2. Because once again, this is the number, n squared plus 1 is the number of divisors we have. We divide that by 2, and the base is going to be the number itself. So it tells us that log 10 of this number is equal to 792. And basically the log 10 and the base 10 cancel out. So this just leaves us with n and exponential properties. If we have something raised to another, if we have one exponent raised to another, it's just the product of those two. So we have n times n plus 1 squared over 2 is equal to 792. We get that n times n plus 1 squared is equal to 1584. We know that since we're asking for integer divisors, that n is going to be an integer, so we can kind of guess or check, or we can solve this cubic if you want. But basically, we come to the conclusion that n is equal to 11. And you can verify if you want, 11 times 144. So yeah, moving on. Let's talk about GCD and LCM now. Oops, this is a lot of text. Forget that for now. So basically, GCD is the greatest common divisor. And of two numbers, it's basically the greatest number that divides both of them. So if we have something like the GCD of 36 and 90, this would be 18 because it divides both of them, and there's no greater number that divides both of them. And I guess traditionally, quote unquote, you would do this by listing the numbers out, or listing the factors out and then comparing them. And you would do the same for LCM. If you have LCM, let's say 12 and 15, this is equal to 60. And if you don't notice this right off the bat, you just have to list out the multiples of 12, list out the multiples of 15, and see which ones of them or what's the smallest number that they have in common. And you'll see that it's 60. But that's a pretty tedious way to do it. So how do we speed this up? And the way we do that is we make use of this jumbled mess of text right here. I'm not gonna try and explain that. I'll just give it to you straight. Basically, if we have one number, let's go back to our example of 36 and 90. We prime factorize it. This is 2 squared times 3 squared. And 90 is, let's see, 2 times 3 squared times 5. Or no. Yeah, that's right. Basically what we do is we take a look at the prime factorizations of the two numbers, and then we take the smallest of the two exponents. Or let me rephrase that. So for every prime factor that they have in common, or even they don't, let's just fill in this is 5 to the 0. For every common prime factor, we take the smaller exponent. So here the smaller exponent would be 1. So we take that. Here the smaller exponent, well, it's the same. It's 3 to the 2 or 3 to the 2. So let's just take 3 to the 2. And then here the smaller exponent is 5 to the 0. So the product of this is 18. And that's how we get the GCD from the prime factorization of numbers. And this is especially useful for larger numbers or variables, where it's not easy just to list stuff out. And basically, the important thing to note here is that if you don't have a prime factor in one that the other has, you just fill it out with exponent of 0. And a similar process works for the LCM. If we have these numbers, instead we just look for the larger exponent. So this time we'll be taking 2 squared. And again, 3 squared is the same on both sides, times 3 squared. And the larger exponent is 5 to the 1. And this would give us the LCM of these two numbers, which is 4 times 9 times 5, which is 180. That's the LCM. So the GCD, you take the smaller of the exponents. The LCM, you take the larger of the exponents. And basically, that's how you calculate it. So let's try this problem real quick. Let me move it over. There we go. As for the quotient when the LCM of these two numbers is divided by the GCD. So I'll go ahead and prime factorize this for you since this is a pretty large number. 6468 is equal to 2 squared times 3 squared times 7 times 11, and 1456 is equal to 2 to the 4 times 7 times 13. So if we want the GCD, the two numbers, we take the smaller exponent of every prime factor they have in the union of their prime factor. I guess that'd be a good way to state it. So the smaller one here is obviously 2 squared. The smaller of the threes, well, the second number doesn't have a 3, so that's going to be the one we want. The 7s are the same, and there's no 11 in the second number and no 13 in the first number, so we can just not include either of those. So this is just equal to 28. And then we look at the LCM. This time we look at the largest of the larger of the two numbers, or the two exponents rather. So the larger one here is 2 to the 4. And then we have 3 squared here. There's no 5 in either of them, so we don't have to worry about that. The 7s are the same. The larger 11, quote unquote, because remember this is times 11 to the 0 and this is times 11 to the first, would be 11 to the first. And same goes for 13. And I'm not going to calculate this out because the question asks us for the quotient of these two numbers. So if we divide these two numbers, this would cancel out. This would become 2 squared. This would cancel out. So the answer is actually 2 squared times 3 squared times 11 times 13. Or wait, hold on. Sorry, I misfactorized this. This is 7 squared. That's what I did wrong. Sorry about that. But the GCD would stay the same since 7 to the first is less than 7 to the second. The LCM would be 7 squared actually. So that would give us 1 7 left over. And then the final answer is 12,012, if you're curious what this mess comes out to. Speeding along, there's this useful formula that involves both the GCD and the LCM. It basically states if we have two numbers, x and y, their product is equal to the product of the GCD of the numbers times the LCM of the two numbers. Let's say like 12 and 15 from before. The GCD of these two is 3. The LCM is 60. So the product of these two, 3 times 60 is equal to 180, which is also the product of 12 times 15, which is 180. So this is useful for, in computational problems at least, if you have one of these given, one of the GCD, one of the LCM given, and you want to find the other one. But this problem, we're going to use it in a slightly more, I guess, creative approach, if you could say that. This problem is from the 2018 AMC 10B. It states how many ordered pairs A and B of positive integers satisfy this equation. AB plus 63 is equal to 20 times LCM of AB plus 12 times the GCD of AB. And what we want to do here is we denote LCM of AB. Let's call that X. And let's call the GCD of A and B something like Y. So we know that AB plus 63 is equal to 20 times, we substitute these values in, 20 times X plus 12 times Y. However, for this formula, remember that the product of the two numbers is equal to the product of their GCDs. So actually AB, which is the product of the two numbers, is equal to XY, the product of the GCD and LCM. So we can substitute this in as well to get XY plus 63 is equal to 20X plus 12Y. Oops. So what we want to do here is we move the variables to the left-hand side to get xy minus 20x minus 12y plus 63 is equal to 0. And let me move the screen down a little. We're going to use Simon's favorite factoring trick like we went over in previous weeks. We get something like, if we factor out the x, we get that x times y minus 20 minus 12y plus 63 is equal to 0. This is equal to x times y minus 20 minus 12 times y minus 20 because we want to create another y minus 20 term. And then we have to add back the negative 20 that we created. So this is equal to 240 plus 63 is equal to 0. And so basically this gives us x minus 12 times y minus 20. And if we move the two terms to the right-hand side, this is equal to 177. So another important thing to keep in mind is that the LCM is greater than the GCD. So that means that x is going to be greater than y. So unless these two terms are pretty close, this x minus 12 term is going to be greater than the y minus 20 term. So 177 only has, I think, 2 ways to distribute it out. This can be 177, this can be 1. Or the other case is if we have x minus 12 is equal to 59 and y minus 20 is equal to 3. And so if we calculate x and y from this, x is equal to 189, y is equal to 21, and then this one, x is equal to 71, and then y is equal to 23. And you would think that now we have 2 sets of answers. However, a second important thing to remember about the GCD and the LCM is that the LCM has to be a multiple of the GCD. And the reason for that is because, again, we're dealing with the same prime factors to the different exponents. So therefore, the GCD will always be able to divide into the LCM. And if you see in this case, this is clearly not true. So we omit this case. And in the first case, 189, that's equal to 21 times 9. So that actually satisfies our condition. So now we have our x and y. So now let's calculate a and b. So if we have the LCM, or let's move this down a bit first. The LCM of a and b is equal to 189, and the GCD of a and b is equal to 21. And since 189 is already 9 times 21, it's pretty evident here that A is going to be 189 and B is going to be 21. And the problem asks for the number of ordered pairs of A and B which satisfy this. And we can also flip these two as well to get B is equal to 189, A is equal to 21. So this gives us 2 total cases. Now for the last topic that we'll be covering today, we're going to be going over the Euclidean algorithm. So Euclidean algorithm is a way to simplify GCD calculations to make it so that it's not so tedious, I guess. And it basically states that if we have a number, 2 numbers, one of which is bigger than the other, let's say x is greater than y, then the GCD of those 2 numbers is equal to the GCD of their difference along with the smaller number, which is y. And this can be applied multiple times in a row as well. So let's say we have something like GCD, GCD of 21 and 2, right? I mean, this is an easy case, but I'm just using it for demonstration. Then this would be GCD 19, 2, 17, 2, ... to 1, 2. Well, we could speed this up by just saying that 21, if we subtract all the 2's we can from it, this is equal to 2 times 10 plus 1. So we just jump straight to 1, because we can subtract 2 10 times. So this is just GCD 1, 2. And that's a way to speed this up. So let's try this problem. Last problem we'll be doing today. It's from the 1986 AMY. It asks for the largest positive integer n for which n cubed plus 100 is divisible by n plus 10. So the way to approach this is we're going to be using GCD, which might be, I guess, unexpected at first, but one cool thing you can do with GCD is if you take the GCD of these 2 numbers, if it's equal to n plus 10, then that means n plus 10 is divisible by n cubed plus 100. So we basically want this to be true. And as for how we're going to simplify this, we're going to use Euclidean algorithm. So basically, this is equal to, let's subtract out n squared copies of n plus 10. So this is equal to GCD of n cubed plus 100, this expression. And then we'll subtract out n plus 10, n squared times, comma, n plus 10. So this is equal to GCD of n cubed plus 100 minus n cubed minus 10 n squared, comma, n plus 10. And this is equal to GCD of negative 10 n squared plus 100, comma, n plus 10. So what we basically did here was we repeatedly applied Euclidean algorithm, but instead of just applying it once, we do it n squared times. Now we're not done yet. Let's move the screen a bit down, and then let's once again subtract n copies, or rather 10 n copies. And the reason why I'm choosing these numbers is because we want to cancel out the terms of greater exponents, right? So first we canceled out this n cubed. Now we want to get rid of this n squared. So actually we're not going to subtract, we're going to add copies, which also works. It's like subtracting negative copies. So this is equal to GCD of negative 10 n squared plus 100 plus n times n plus 10, comma, n plus 10. And this is equal to GCD of, or rather 10n squared, my bad. This is just going to cancel out, and we're left with 100 n plus 100, comma, n plus 10. And finally, we want to subtract n plus 10 100 times. So it's equal to GCD of 100 n plus 100 minus 100 times n plus 10, comma, n plus 10. So this is equal to GCD of
negative 900, comma, n plus 10. And from the beginning, remember that this value is supposed to equal n plus 10. So that just means that n plus 10 has to divide negative 900. And the greatest value of n, which makes this possible, is if n plus 10 is equal to 900, so therefore n is equal to 890. And that's our final answer. So for this problem, we basically just applied Euclidean algorithm over and over using variables to eliminate the terms that we couldn't deal with. So the n cubed, the n squared. Once we eliminated those, we got it down to this final expression right here. And then we just knew that n plus 10 had to divide negative 900. And from there, the problem was easy. And so yeah, that's all I have for today. Sorry about the technical difficulties. That was yeah, not planned. Hopefully it won't happen next time. Yeah, that's all I have for this class. A lot of people are telling me to charge my battery. Yeah, that's a good idea, but yeah, it's all planned. It's all planned. You know, I end at 5%. It's all planned. All right, I'm gonna stop the recording now. Thanks for coming, everyone.